Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for day 15 of Advent of Code. Just to maybe give you some hope, or to, I don't know, let you know that we're all learning and growing, and however you solve it is a good way to solve it. I just wanted to show you this. It's a little. I was doing another puzzle offline just for fun, and I had to like turn a flat 2D surface into like a cube so that you could like walk across it, and it was easier for me to solve the problem by like cutting this out and then like putting the faces together so I knew which ones connected to which and how they changed. Anyway, that's all just to say keep working at it, keep getting better. The other thing is, besides loving your comments, keep them coming, is there's another website, Everybody Codes, I think, like that, something like that. And so maybe we'll try that after I finish 2016, just to keep solving puzzles, see how it goes. It sounds like they may start up soon with their new year. They're on their second year. So anyway, we'll give it maybe we'll give that a shot. So anyway, let's get solving. This one is Timing is Everything. The halls open into an interior plaza containing a large kinetic sculpture. The sculpture is in a sealed enclosure and seems to involve a set of identical spherical capsules that are carried to the top and allowed to bounce through the maze of spinning pieces. Okay, so it's like a Plinko or whatever it's called. Part of the sculpture is even interactive. When you press a button, a capsule is dropped and tries to fall through the slots in a set of rotating discs to finally go through a little hole at the bottom and come out of the sculpture. If any of the slots aren't aligned with the capsule as it passes, the capsule bounces off the disc and soars away. You feel compelled to get one of those capsules. The discs pause their motion each second and come in different sizes. They seem to each have a fixed number of positions at which they stop. You decide to call the position with the slot 0. Okay, so that's like open at 0. And count up for each position it reaches. Furthermore, the discs are spaced out so that after you push the button, 1 second elapses before the first disc is reached, and 1 second elapses as the capsule passes from one disc to the one below it. So if you push the button at time 100, then it reaches the top disc at time 101, the second disc at 102, and the third at 103, and so on. The button will only drop a capsule at integer time, no fractional seconds allowed. For example, at time 0, suppose you have this arrangement. So disc 1 has 5 positions and starts at position 4. Disc 2 has 2 positions and starts at position 1. Okay, I'll keep reading this, but I think, well, let's see. If you press the button exactly at time 0, the capsule would start to fall and would reach the first disc at time 1. Since the first disc was at position 4 at time 0, by time 1 is ticked 1 position forward. As a 5 position disc, the next position is 0, and the capsule falls through the slot. Then at time 2, the capsule reaches the second disc. The second disc has ticked forward. At this point, it started at position 1, then continued to position 0, and finally ended up at position 1 again. Because there's only a slot at position 0, the capsule bounces away. If, however, you wait until time equals 5 to push the button, then when the capsule reaches each disc, the first disc will have ticked forward 5 plus 1 equals 6 to position 0, and the second will have ticked 5 plus 2 equals 7 to position 0. In this case, the capsule would fall through the discs and come through the machine. However, your instruction has more than 2 discs. You've noted their positions in your puzzle input. What is the first time you can press the button to get a capsule? Okay, so I think you can solve this 2 ways if I had to guess. This looks like a Chinese remainder theorem. The idea behind that is if you have a set of constants and some moduli, which is what these are, you can calculate a specific value, in this case time t. So we may look at that if we need to for part 2, but we can also just sim this, and I think we can sim it fairly easy. So yeah, there you go. Just to make sure we understand what's happening is you know, they're all ratcheting and opening up, and we want them all to be at like 0 at that time. So I think we can probably try and sim this. Let's see here. And then we can do the Chinese, maybe we can do it after we've solved it. Or potentially if it's too slow, then we can try and do that. But we're just going to get 2 values. So this is going to be iter lines map. Let parts equal L dot split white space. What is my puzzle input? There's 6 of them. Okay. So we want to get the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3 and 11. We got to get rid of those periods. Like that. I'm inclined. I want to do this one first because it's the position, and then this is the modulus. Like I think they call these the constants A, and then these are the modulus M. Just in case we ever have to do the other way. Can I do this all in like a single pipeline? So if I do like this, dot find. What does this do? Searches for an element of iterator that satisfies a predicate. Find takes a closure, returns true or false. So I think I can do a find dot unwrap, right? Like the first one we find will be the answer. And so this is time t. So I want all of them to be at position 0. And so that's like, let's see, it would be input dot iter dot all. I need to enumerate them. Enumerate. So I'm going to get I pause modulus like that, I think. And it's going to be, so all of them need to be equal to 0. And what is it that needs to be 0? It's time plus pause plus I plus 1. Modulus or modulus equals 0. I don't know if I have to do those things. Oh, I'm missing one right here. I mean, is as simple as that? The idea is go through all the times. And for each time, go through all our inputs, enumerate over them all. All of them have to be equal to 0. And what is all of them? Where my time plus my position plus where I am on the thing plus 1. I think it's plus 1, right? Because, like, let's say it's time 0. This is pause position 0. Sorry, it starts at position 0. I is 0. But it will have dropped at time 1, so I want this to be position 1. So I think that is right. What are the odds? Okay, that's the right answer. Not too bad. And it does finish fast. It finishes in microseconds. So maybe we don't have to do the CRT. After getting the first capsule, it contained a star. What great fortune. The machine detects your success and begins to rearrange itself. When it's done, the discs are back in their original configuration as if it were time 0 again. But a new disc with 11 positions and starting at 0 has appeared exactly 1 second below the previous bottom disc. With this new disc and counting again starting from time 0 with the configuration or puzzle input, what is the first time you can press it? Okay, so for part 2 then, it looks like we're just adding another disc. So I think we do the same thing. Oops. But now we do let input equal input dot iter dot. We just clone it and do input dot push. What were the values? Starts at position 0 with mod 11. So it's like 0, 11. Is this going to make it like take forever? No, it doesn't. This is in 4 milliseconds. Assuming it's still correct. Okay. Yeah, I mean, from simming it, that's actually not that hard. We are kind of lucky that we can do like these type of things, so I felt like it was really easy to do this. Although again, unwrapping the logic isn't too tough. I'm tempted to try the CRT. Let me just look really quick. Chinese remainder theorem. Yeah, I've looked at this before. So it looks familiar to me. I'm sure we've done a puzzle like this before. The idea behind it is if you have a bunch of equations like this, but they have to be pairwise coprime, which I think we have, right? That just means like all of these have to be prime and they can't be the same prime number, I think. This is where I don't know the math part of it, so I just have to trust that this is correct, and I'd be doing a lot of copy and pasting. But then you potentially run this, which is just over the number of congruences. You have to do mod inverse. I think that's the multiplicative one, multiplicative module inverse. I think we've done that before, right? Yeah, you had to solve for the GCD, and then you do this thing of the GCD. Here's how you solve for GCD. So I think this would work too, but let's see. There's just a... Looks like there's some crates that already provide it. What is the ring algorithm? So like here's one that they say has already done it. I give you give it the U and the M. These would be the moduli, presumably, and these are like the states. What does the source code look like? It'd be nice to understand exactly how these work. I'm willing to try this. Where else did it say it found it? Oh, that's the one I was just looking at. Bubble math. In pure Rust. Primality test. Next prime. Oh, this is over 2 moduli. So that one may not actually work. Yeah. That one actually won't work. Implement your own function. I mean, I'm inclined just to like copy and paste this one and try it. Okay, I'm going to put it over here just so I can see. And we'll give it a try. I'll try it once really quick just to see if it works. See if I get the same answer. Okay. P1 CRT. Like that. So we need to get the big M. Which is like the second one. And do the product of it. Is this going to be like a big thing? I don't know if we have to do negative math. But we may have to do like big math while we're doing our stuff. We'll see. Maybe it'll never be that big, but we'll try it. So it's a for loop where I'm scanning. So I think I can actually do where I'm like folding a value in. So I actually think I can do input dot iter dot fold. We start at 0, I128, and we'll get an ACK and AM. I think they're called A and M. And so it is going to be let mi equal the top m over this m. I know it doesn't like me doing this. We'll just leave it like this. We can find a new name for it. And then let ni equal mod inverse. We'll have to figure that out. mi over m. Oh no, mi of m. And then it is ac plus a times mi mod big M times ni mod m again. How does fold work? Like, do I actually want to use fold? I don't remember fold. I think this is what I return in fold. Okay, let's just do U sides for now, so we don't have to. Surely U size is enough, right? We'll see. I mean, this is one of those things where I just don't know enough about it, and I'm just gonna have to do the math and hope that it works. There might be a mod inverse package, though. Let's see. Then we don't have to figure it out. There is. Did I do that wrong? Yeah, see, I've done it before somewhere. I have to like reload this, I think. Surely I get the right one back. I don't get the right answer, though. Okay, let's make sure I'm doing it right. It's mi is big M over M. Ni is mod inv of mi over M. I mean, these could be different in this one. 129.9. Oh, is it off because I think I need to move these like I did with the other thing. Like that. What doesn't it like? Oh, is it this? Can I do this? Nope. That's worse. I mean, I guess I don't know if it's worse or better. It's not gonna like this. And this. Like, I'm just wondering if I have to have like a much bigger number. Oh, I still do this as a U size and then cast it after as. Nope, that's still wrong. This isn't too big, right? As I-128. This would, I mean, this is probably pointless of me doing this. And maybe we just don't even continue down this path. I'm sure it's a CRT, so it does beg the question why it wouldn't work. Big M, map product of M's. Enumerate fold start at 0. So my A is A plus I plus 1, just like I did here. AC plus AI. Here, I'll slide this over so you can kind of see what I'm looking at. So I'm trying to compare these. It's the accumulator, which is the solution, plus A times MI modulo big M times NI modulo big M. Okay, I mean, I think I'm doing that right. Still not getting the right answer, though. I'm not convinced it's the 128 thing. Again, we could try doing this. Sometimes they switch them around. No. Like, I'm sure they're co-primes. Right? That's what our puzzle input was. 7, 13, 3, 5, 17, 19. Those are all co-primes, I think. Okay. Should we see if like ChatGPT can do it? I just don't know enough about it that I don't know where I might be making my mistake. It's possible that I'm switching values around. Or maybe I'm... This is nothing like what I had done, right? So this will probably be a day then if this actually solves it, that you like, okay, I'm definitely coming back to this day so we can see how it works. RM. I think that is in the right order. Does that solve it? No, it blows up. Okay, dot unwrap. What does it return? Why does it return a thruple? R and M? I mean, that's not... Okay, let's just see if it can solve the big thing. And if not, maybe the CRT isn't here, or maybe we'll have to just come back to it. I don't want to spend like an hour and a half figuring a bug in a algorithm that I'm not familiar with. P plus T plus I equals 0. So T da da equivalently, that gives you the congruence per disk. Solve the system with CRT. I mean, we'll definitely have to read more about this because I just don't know enough about it to say if it's doing what I, you know. Extended GLC, normalized CRT, earliest time for disks. Okay, I mean, that does solve it, and it solves it way faster. I guess we just do this, and then we do this, and then we do this. So we just call these solve. Okay, so it is giving us the right answers. I mean, it is faster for sure, especially part 2. So it would be worth learning this. We should probably just take some time to learn this at some point. So what does this do? We take our pairs. We do some math. Okay, so this is the part I was missing. We have to do some math on them. So can we, let's read. Day 15 reduces directly to a system of modular equations and solve cleanly with the CRT. Let disk I, numbering start at 1, have M positions and be at position P at time 0. If you push the button at T, then the capsule reaches disk I at T plus I. You need that disk to be at position 0 at that time. Yes, okay. So time. Oh. So I don't know if you remember, but like right here, when we were calculating these things right here, I was just calculating this and assumed that was the new position. But what ChatGPT is saying here is, oh, you actually need to do the math. So you have this equation. Now can you solve for time? And it turns out that T is this, which is this. So then when you look here, like that's what's happening right here is we're taking the disks and turning them into, it's the same thing. We're still going to do a CRT, but we're now doing the CRT for time. Whereas the previous CRT was like for A or whatever, right? So this some constant K, this number right, the previous number we got was not looking for the right thing. That's essentially, this gives us one congruence per disk. Solve the system with CRT. And so I think this is probably RM, normalize RM. This is a different algorithm than what we used. Okay, I think we'll stop it here. But so I'll submit it like this. This will definitely be a thing to add to the list to learn more about the Chinese remainder theorem and like why it works. I think the reason why, again, let's look like part 1 took 8 minutes and part 2 took 1.5 minutes. And then we've spent 33 minutes trying to do this Chinese remainder theorem. I think it's worth knowing it, though, is what I should say. I'm sure we've gotten CRTs before. And you can imagine if the number was the number of like disks in this puzzle was like 20 times as big. Finding the actual one where they match may require you to actually know what the Chinese remainder theorem is. So I think when we do a recap, we'll definitely make this one of those days where we actually learn what this does. But anyway, there you go. I'll submit this. Let me know. Maybe you know enough. You know about the CRT, and I don't know. Maybe there's a video somewhere that explains it, why it works, in more details. I've just seen it before, again, because I think after I've solved things, or maybe I used some package that did it because I knew that's how it solves. So yeah, I'd love to know how you did it. Anyway, there you go. Thanks, everybody. We'll talk to you next time. Bye.